You are here. You believe this to be a simple statement of fact, a declaration of presence. You occupy a volume, a set of coordinates on a map that is both personal and cosmic. You exist in a place, and you are now. This, too, feels certain. You are held in the amber of a fleeting moment, a tick of a clock that moves relentlessly, unstoppably, forward. You exist in a time, place and time, space and duration, the two pillars upon which your entire reality is built. They are the stage, and you're the player. They are the canvas, and your life is the brushstroke. They are so fundamental, so utterly and completely self-evident that to question them feels like madness. It feels like asking if up is truly up, or if a circle is truly round. But we must ask. We must pull at the threads of this fabric we call existence. What if the stage is not a stage at all? What if it is part of the play? What if the canvas is not a canvas, but merely a pattern created by the paint itself? What if space and time are not the containers of reality, but are instead properties of reality? What if they are not the rigid, absolute certainties you feel in your bones, but something far stranger, far more elusive, and perhaps not even fundamental at all? This is the journey we are on, a journey to the very edge of intuition, to the place where our senses fail us, and only the most exquisite and terrifying ideas can guide us. We are going to deconstruct the world. We're going to dismantle the clock and unroll the map until we find what lies beneath. Prepare yourself. The floor beneath your feet is about to vanish. The clock on your wall is about to become a liar. You feel solid. You press your hand against the table, and it feels undeniably real. It resists. It has substance. You move through a room, and you feel the air, the distance between objects. This is the world your senses report to you, a world of things and places. This report is a lie. It is a convenient fiction, a user interface for a reality so complex and so alien that your mind has evolved to shield you from its truth. The solidity you feel is an illusion. The chair you sit on, the ground that supports you, they're almost entirely empty space. The atoms that make up that chair are themselves phantoms, 999.9999% void. The tiny, frantic nucleus, the buzzing cloud of electrons. These are less like tiny marbles and more like localized disturbances in a field, wisps of probability. The feeling of solidity is not a property of substance. It is the protest of electromagnetism. It is the language of forces. The electron shells of the atoms in your hand are repelling the electron shells of the atoms in the table. You are not touching the table. You are being pushed away by an invisible field, a ghostly barrier that your brain interprets as solid. You are built from this emptiness. You are a walking, thinking, feeling collection of coordinated voids held together by mathematics and whispers of force. And what of the space that this emptiness occupies? That grand, silent void between the stars, between the walls of your room, between the atoms in your own body? You perceive it as a neutral backdrop, a nothingness, an empty arena waiting for something to happen within it. This, too, is a profound deception. Space is not nothing. The vacuum of space is not empty. It seethes with a furious, roiling energy. It is a cauldron of potential where particles of matter and antimatter flash into existence for imperceptibly small fractions of a second, borrowing energy from the future before annihilating each other in a puff of silent light. They are called virtual particles, but their effects are very real. They're the quantum foam, the static of reality itself. This is the first layer of truth. The world is not made of things. It is made of interactions. And the emptiness is not empty. It is full of ghosts. So, if our most basic intuitions about solidity and emptiness are wrong, what does that say about the very stage on which these illusions play out? What truly is space? And what truly is time? To answer this, we cannot stay in the now. We must travel back. We must journey into the minds of the giants who first dared to ask these questions, who first tried to draw a map of God's mind. We must go back to a time of intellectual revolution, when the universe was being redesigned. The year is 1715. Two of the greatest minds in human history are locked in a battle. Not a battle of armies or empires, but a battle of ideas, waged through letters crossing the English Channel. On one side is Isaac Newton, the colossus of physics, the man who uncovered the laws of motion and gravity, the architect of a clockwork universe. On the other side is Gottfried Wilhelm Leibniz, the brilliant philosopher, mathematician, and polymath, a man who saw the universe not as a machine, but as a symphony of relationships. Their dispute, on the surface, seems abstract, philosophical, almost theological. But at its heart is the most fundamental question one can ask about the world. Is space a thing, or is it just a description? Imagine a completely empty universe. No stars, no planets, no atoms. Nothing. Just an infinite black void. Now, ask yourself, does this void exist? Newton would have answered with a resounding yes. For him, space was absolute. It was a real, physical entity, an infinite container that existed independently of anything within it. He called it God's sensorium, the medium through which God perceived the universe. It was an eternal, unchanging, three-dimensional grid. It was the absolute stage. You could remove all the actors, all the props, all the lights, and the stage itself would remain waiting. This idea feels intuitive. It is the way you experience the world. You move through space. The room exists whether you are in it or not. Newton's absolute space provided the fixed background against which he could define his laws of motion. An object has an absolute velocity, a true speed and direction relative to this fixed cosmic grid. Without it, he argued, how could you talk about true motion? How could you define acceleration? To prove his point, he proposed a simple thought experiment. Imagine a bucket of water hanging from a rope in that empty void. The bucket is still. The water is flat. Now, twist the rope and let it spin. At first, the bucket spins, but the water inside remains flat. Then, slowly, friction catches up. The water begins to spin with the bucket, and as it does, its surface becomes concave, climbing up the sides. Newton asked, what is the water pushing against? There is nothing else in this universe. It cannot be spinning relative to the bucket, because at the moment of maximum concavity, the bucket and water are spinning together, with no relative motion between them. Yet the water is curved. Why? His answer was triumphant. The water knows it is spinning because it is accelerating with respect to absolute space itself. The invisible, immutable grid of space is exerting a real, physical effect on the water. It proves that space is a real thing, a substance with its own independent existence. For Newton, the case was closed. Reality had a permanent address. But from across the channel, Leibniz cried foul. For Leibniz, the idea of an infinite, empty container was not just wrong, it was nonsensical. It violated his most cherished principle, the principle of sufficient reason, which states that there must be a reason for everything to be the way it is and not otherwise. He posed a counterargument. If Newton's absolute space is real, then imagine God creating the universe. He has to decide where to place it. Should he place the entire cosmos here, or 3 feet to the left? If space is just an empty, uniform grid, there is no difference between here and 3 feet to the left. There is no property that distinguishes one location from another. Therefore, there is no sufficient reason for God to choose one over the other. The very idea of placing the universe in space becomes an absurdity. Similarly, God could have created the universe and then shifted the entire thing instantaneously to another location. According to Newton's own laws, nothing would change. The bucket would still spin, the planets would still orbit. No experiment could ever tell the difference. So why, Leibniz asked, would God create this redundant, unobservable entity called absolute space? It was an unnecessary and illogical piece of cosmic furniture. For Leibniz, space was not a container. It was relational. Space is nothing more than the set of all spatial relationships between objects. It is a system of ordering. There is a distance between the Earth and the Moon. There is a direction from the Sun to Jupiter. Space is the collection of all such distances and directions. If you remove all the objects from the universe, you also remove all the relationships between them. And if you remove all the relationships, you remove space itself. In an empty universe, for Leibniz, there's no space. There is not even a where the question itself is meaningless. In the bucket experiment, Leibniz would argue that the water is not accelerating with respect to absolute space. It is accelerating with respect to all the other matter in the universe, the distant fixed stars. In a truly empty universe, with no other matter to serve as a reference point, the concept of rotation would be meaningless, and the water would never become concave. This was the great schism, Newton's absolute stage versus Leibniz's relational dance. Is reality built upon a fixed, eternal framework, or is the framework an emergent property of the components themselves? Is space the landlord, or is it just the address book? And what a time! The argument extended here, too. For Newton, time was also absolute. It flowed equably without relation to anything external. It was a universal clock, ticking at the same rate for everyone and everything, everywhere in the cosmos. It was the metronome of God, relentless and sovereign. There was a single true now that encompassed the entire universe. Your now was the same as the now for someone in the Andromeda Galaxy. Leibniz, again, found this to be a violation of reason. Absolute time was an unobservable fiction. All we can ever measure is the duration of events relative to other events. A heartbeat relative to a pendulum swing. A planetary orbit relative to the decay of an atom. Time, for him, was not a river we flowed in. It was simply the order of events. This happened, then that happened, then another thing happened. Time is the grammar of causality, the before and after that connects the story of the universe. If all events in the universe were to stop for Leibniz, time itself would stop. If they were all to suddenly run at double speed, nothing would change, because all the relationships between events would remain the same. The concept of a universal, absolute tick was superfluous. For 200 years, Newton won. His physics was so stunningly successful, so powerful in its predictions of everything from falling apples to orbiting moons, that his philosophical framework was accepted along with it. The universe was a grand machine set in motion by a divine engineer on a fixed stage of absolute space and time. It was elegant, powerful, and comforting in its certainty. Humanity had found its place. We knew where we were, and we knew when we were. And then a young man working in a patent office in Bern, Switzerland, began to think about trains and lightning bolts. And in doing so, he shattered the clockwork universe forever. His name was Albert Einstein, and he was not a Newtonian architect or a Leibnizian philosopher. He was a new kind of archetype, the breaker of clocks. The problem that obsessed Einstein was not grand or cosmic, but deceptively simple. It arose from the work of James Clerk Maxwell, who had unified electricity and magnetism into a single, elegant theory. Maxwell's equations predicted that light was an electromagnetic wave and that it always traveled at a specific, constant speed, roughly 300,000 kilometers per second. Always. This was the word that caused the crack in Newton's universe. Think about it. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the platform sees the ball moving at 120 kilometers per hour. Speeds add up. This is common sense. It is Newtonian physics. But Maxwell's equation said that if you're on a spaceship traveling at half the speed of light and you turn on a flashlight, the beam of light leaving your flashlight still travels away from you at the full speed of light. And an observer watching you pass by would also measure that same beam of light traveling at the exact same speed. Not 1.5 times the speed of light, just the speed of light. This is impossible. It is a paradox that violates the very logic of motion. How can something's speed be the same for everyone, regardless of how they're moving? It's like two cars driving away from each other, yet each driver measures the other car as being right next to them. For years, physicists tried to solve this. They imagined a luminiferous ether, a fixed, invisible substance that filled all of space, the medium through which light waves traveled. The speed of light was constant only with respect to this ether. But experiment after experiment failed to detect this ether. Nature refused to show us a preferred frame of reference. Einstein's genius was not to fix the paradox, but to embrace it. He elevated it to a principle. He said, what if the speed of light in a vacuum is absolute? What if it is the one true constant in the universe? If that is true, then something else must give. Something else must be relative. That something was space and time. Einstein realized that for the speed of light to remain constant for all observers, their measurements of distance and duration must change. Speed is distance divided by time. If the speed is fixed, then distance and time themselves must become flexible. They must stretch and shrink depending on your motion. This was the heart of his 1905 theory of special relativity. It was a devastating blow to Newton's absolute world. Imagine two people with perfectly synchronized clocks. One stays on Earth, and the other flies off in a super-fast spaceship, travels for a while, and then returns. When they meet again, their clocks will no longer be synchronized. The astronaut's clock will have ticked more slowly. For the astronaut, less time will have passed. This is not a mechanical error. Time itself has slowed down for the moving observer. This is called time dilation. The faster you move through space, the slower you move through time. And it's not just time. Space contracts as well. The spaceship, as it speeds past, would appear shorter to the observer on Earth in the direction of its motion. From the astronaut's perspective, the universe in front of them has shrunk. This is length contraction. This changes everything. There is no universal clock. There is no absolute. Now the idea of simultaneity is destroyed. If you and I are moving relative to each other, my now is a different slice of reality than your now. Imagine a distant star exploding. An observer flying towards the star will see the explosion happen before an observer flying away from it. Both are correct. There is no single, objective moment of the event. Time is not a universal river. It is a collection of personal streams, each flowing at a different rate. So what did this mean for the great debate between Newton and Leibniz? In a way, Einstein sided with Leibniz. There is no absolute time. Time is relative to the observer. But he did something far more radical. He didn't just make time relative, he stitched it together with space. His former professor, Hermann Minkowski, realized the profound implication of this. He declared, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This union is space-time, a four-dimensional continuum, where three dimensions are space and the fourth is time. Everything that has ever happened or will ever happen has a specific location in this space-time block. Your birth, your reading of this sentence, your death, they're all just points in a vast, static, four-dimensional landscape. This sounds strange, almost fatalistic. But for physics, it was a revolution. The one absolute thing that emerged from Einstein's theory was not space or time, but the interval in space-time between two events. All observers, no matter how they are moving, will agree on this single, invariant measure. Special relativity had demoted Newton's absolutes and created a new, unified absolute, space-time. But Einstein was not done. His first theory only dealt with constant, uniform motion. It did not include acceleration, and it did not include gravity. For the next 10 years, Einstein wrestled with gravity. Newton had described it as a mysterious force acting at a distance, an invisible rope pulling objects towards each other across the void of space. But how did the sun tell the Earth to orbit? How did that information travel instantaneously across 150 million kilometers of emptiness? This spooky action at a distance had always bothered Newton himself, and it deeply troubled Einstein. His breakthrough came from another simple thought experiment. He called it his happiest thought. Imagine a man in a closed elevator in deep space, far from any gravitational pull. The elevator is being pulled upwards by a rope at a constant acceleration. The man lets go of a ball, and it falls to the floor. If he stands on a scale, it registers his weight. For him, inside his closed box, the effects of acceleration are indistinguishable from the effects of gravity. Now, imagine the same elevator is at rest on the surface of the Earth. The man again drops the ball. It falls. He stands on a scale. It shows the same weight. There is no experiment he can perform inside the elevator that can tell him whether he is accelerating in empty space or sitting still in a gravitational field. This is the principle of equivalence. Gravity and acceleration are two sides of the same coin. And if gravity is equivalent to acceleration, and acceleration is motion, and motion affects space and time, then gravity must affect space and time. This was the key. Gravity is not a force in space-time. Gravity is the curvature of space-time. This is the general theory of relativity, Einstein's masterpiece. It is a complete redesign of the cosmos. The Newtonian stage is not just flexible. It is an active participant in the drama. Mass and energy tell space-time how to curve, and the curvature of space-time tells mass and energy how to move. The Earth is not being pulled by the sun. The sun, being massive, creates a deep dimple, a valley, in the fabric of space-time around it. The Earth is simply following the straightest possible path through this curved geometry. It is rolling around the inside of the sun's space-time well. What we perceive as the force of gravity is just the shape of reality itself. The universe is no longer a clockwork machine. It is a cosmic trampoline. This theory made astonishing predictions. It predicted that light from distant stars should bend as it passes by the sun, because it is following the curved space-time. During a solar eclipse in 1919, expeditions confirmed this, and Einstein became a global celebrity overnight. The universe was not what we thought it was. It also predicted that time should run slower in stronger gravitational fields. A clock at sea level ticks ever so slightly slower than a clock on a mountaintop. This is not a theoretical curiosity. Your GPS system has to account for this effect. The clocks on the satellites, being in a weaker gravitational field and moving at high speed, tick at a different rate than clocks on the ground. Without correcting for Einstein's theories of relativity, your GPS would be inaccurate by several kilometers every single day. So, where does this leave our epic debate? Is space a thing or relation? Einstein's space-time is a dynamic physical entity. It can bend, it can ripple, it can expand. It is far more like Newton's absolute container than Leibniz's relational web. It acts on matter, and matter acts on it. When two black holes merge, they send out gravitational waves, ripples in the fabric of space-time itself, that we have now detected on Earth. Space-time is a thing. It has substance. Newton, it seems, was closer to the truth. But the victory is not so clear. General relativity also has a Leibnizian flavor. The geometry of space-time is determined by the matter and energy within it. Without matter, the simplest solution to Einstein's equations is a flat, empty space-time. The stage is shaped by the actors. Furthermore, the theory is background independent in a way that Newton's was not. The laws of physics are the same for all observers, no matter how they are accelerating. There is no preferred frame of reference, no absolute cosmic grid to point to. Einstein gave us a beautiful, geometric, and deeply strange universe. A universe where space and time are a single, malleable fabric. He had seemingly resolved the ancient conflict by weaving both threads together. But the universe is stranger still. Einstein's cosmos, for all its weirdness, is smooth. It is continuous. It is a flowing, geometric tapestry. But there is another realm of physics, a realm that he himself helped to create but could never fully accept. A realm that operates on a completely different set of rules. The quantum realm. When you zoom in on Einstein's beautiful space-time fabric, when you get down to the smallest possible scales, the picture shatters. The smooth continuity breaks down. The elegant geometry dissolves into a chaotic, probabilistic foam. Welcome to the edge of the map. This is where monsters are born. There is a fundamental limit to smallness in the universe. A shortest possible distance, known as the Planck length, which is about 16 times 10 to the power of negative 35 meters. It is a distance so incomprehensibly small that if you were to scale an atom up to the size of the known universe, the Planck length would be the size of a single tree. There is also a shortest possible unit of time, the Planck time. It is the time it would take for light to travel one Planck length. It is the briefest possible tick of a cosmic clock. Below this scale, our concepts of space and time simply cease to have meaning. They are not just hard to measure. They fundamentally do not exist in the way we understand them. The smooth, continuous fabric of Einstein's spacetime is an approximation, a low-resolution image of a much finer, pixelated reality. What is this reality made of? We do not know, but our theories give us haunting glimpses. At this Planck scale, the quantum uncertainty principle reigns supreme. This principle states that you cannot simultaneously know certain pairs of properties of a particle, like its precise position and its precise momentum. The more you know about one, the less you know about the other. This uncertainty applies to spacetime itself. At the smallest scales, the energy of the vacuum fluctuates wildly. Remember those virtual particles popping in and out of existence? Their energy, according to Einstein's E equals mc squared, has mass, and mass curves spacetime. This means that at the Planck scale, spacetime itself is not a placid sheet, but a churning, violent sea. It is a quantum foam of tiny, transient bubbles, wormholes, and black holes, appearing and vanishing in less than a Planck time. In this realm, causality breaks down. The neat before and after of Leibniz's ordering becomes a confused jumble. An effect can precede its cause. The arrow of time loses its direction. The very geometry of space becomes probabilistic. The notion of here becomes fuzzy. A point is no longer a point, but a cloud of potential locations. This is the fundamental conflict of modern physics. We have two incredibly successful theories of the universe. General relativity, which describes the very large, planets, stars, galaxies, and the cosmos, as a smooth, geometric dance. And quantum mechanics, which describes the very small, atoms and particles, as a world of discrete packets, probabilities, and uncertainty. The two theories are utterly incompatible. They speak different languages. They describe different realities. When you try to use the equations of general relativity to describe a quantum-sized object with immense gravity, like the singularity inside a black hole or the state of the universe at the Big Bang, the math breaks. The equations spit out infinities. They tell us that they are no longer valid. This is not just a mathematical inconvenience. It is a profound crisis. It tells us that our deepest understanding of reality is flawed. It tells us that space and time, the very bedrock of both theories, are not what we think they are. Perhaps they are not fundamental at all. This is the most revolutionary, most earth-shattering idea in modern physics. The idea that space and time are emergent properties, that they are not the fundamental ingredients of reality, but are instead a collective effect of something even deeper, something that exists outside of space and time. What does it mean for something to be emergent? Think of temperature. You feel the heat from a fire. You measure the temperature of a room. Temperature seems like a fundamental property of the world, but it is not. A single atom does not have a temperature. Temperature is an emergent property. It is the average kinetic energy of a vast collection of atoms or molecules. It is a statistical description of a system's behavior. It is real, you can measure it, but it is not a fundamental quality of the components. Think of wetness. A single molecule of H2O is not wet. Wetness is a property that emerges from the interactions of many water molecules together. Think of the screen on which you are watching this. It displays a smooth, continuous image. But if you look closely enough, you see that it is composed of tiny, discrete pixels. The continuous image is an emergent property of the arrangement and coloring of these fundamental pixels. What if space-time is like temperature, or wetness, or the image on a screen? What if it is a macroscopic illusion, a user interface generated by the collective behavior of countless microscopic atoms of reality that do not themselves live in space or time? This is a radical departure from everything we have known. It suggests that the answer to the Newton-Leibniz debate is that both were wrong, because they were both asking the wrong question. They were arguing about the nature of the stage, when perhaps there is no stage. So what could this deeper layer of reality be? We're the pixels of space-time. One of the most powerful clues comes from the strangest phenomenon in all of quantum mechanics, a feature that Einstein himself famously derided as spooky action at a distance. It is called quantum entanglement. Imagine you create two particles, say, two electrons, in a special linked state. You can separate these two electrons and send them to opposite ends of the galaxy. The strange thing is this: they remain connected. They are part of a single, indivisible quantum state. If you measure a property of one electron, for example its spin, you'll find it is either up or down with a 50/50 probability. But the moment you measure it and find it is spin up, you instantly know, with 100% certainty, that its entangled partner, light years away, will have spin down. It is as if the first particle instantaneously communicates its state to the second, faster than the speed of light, violating Einstein's cosmic speed limit. But no information is actually being sent. You cannot use this to send a message. It is something deeper. It is a correlation, a connection that seems to exist outside of space. The distance between the two particles does not matter. 10 feet or 10 billion light years. The connection is instantaneous. This suggests a mind-bending possibility. What if entanglement is more fundamental than space? What if the reason the particles seem connected across a vast distance is because, at some deeper level, they are not separated at all? What if the distance we perceive in our emergent space-time is just a clumsy way of describing a more complex, non-spatial connection? This leads to one of the most exciting and provocative ideas in modern physics, encapsulated in the equation ER equals EPR. EPR refers to a famous thought experiment by Einstein, Podolsky, and Rosen that first highlighted the paradox of entanglement. ER refers to Einstein-Rosen bridges, more commonly known as wormholes, theoretical tunnels through space-time that could connect two distant points. The equation ER equals EPR proposes that these two seemingly unrelated concepts are, in fact, the same thing. It suggests that any two entangled particles are connected by a microscopic wormhole. The powerful correlation of entanglement is the quantum manifestation of a geometric connection in space-time. This idea turns our view of reality inside out. We used to think of space-time as the fundamental fabric and entanglement as a weird property of things happening within that fabric. But what if it's the other way around? What if the universe is built not from points in space, but from a vast, intricate web of quantum entanglement? What if geometry, the very shape of space and time, is built from these non-local connections? Imagine a network. The nodes of a network are bits of quantum information. The links between them are entanglement. The more entangled two nodes are, the closer they are. The less entangled they are, the farther apart they are. From this abstract network of information and correlation, the geometric properties we call distance and space emerge. In this view, space is not something you can move through. It is a representation of the universe's entanglement structure. You are not in space. You are a pattern of entanglement in this cosmic web. This is a profoundly Leibnizian idea, resurrected in the language of quantum information. Space is not a container. It is the set of all relationships. But the relationships are not distances. They are quantum correlations. This idea also gives us a new way to think about gravity. The same connections that create the geometry of space also give rise to its dynamics. The tendency for space-time to bend and curve, which we call gravity, might be a thermodynamic consequence of this entanglement network striving for maximum entropy. Gravity, then, would not be a fundamental force. It would be an emergent, statistical phenomenon, like temperature or pressure, an entropic force. Another theory, called loop quantum gravity, paints a similar, yet distinct picture. It takes Einstein's general relativity and applies quantum rules to it directly. The result is that the fabric of space-time is not continuous but is woven from discrete, finite loops. These loops are not in space. They are space. Each loop is a quantum of volume. They connect to form a dynamic network called a spin network. Where the loops intersect, they create nodes, which are quanta of area. The geometry of our world is built from the combinatorial patterns of these connections. Again, we see a relational picture. Space is not a smooth background. It is a network of interactions. Time, in this theory, is also not fundamental. It emerges from the sequence of changes in this network. The discrete moves as the connections rearrange themselves. There is no external clock. There is only the ceaseless dance of the network reconfiguring itself. And what of the holographic principle? This is perhaps the most bizarre and counterintuitive idea of all. It suggests that the reality we experience in three spatial dimensions may be nothing more than a projection, a hologram, encoded on a two-dimensional surface at the edge of the universe. This idea arose from studying the physics of black holes. It was discovered that the amount of information you can cram into a black hole, its entropy, is not proportional to its volume, as you might expect. It is proportional to the surface area of its event horizon. It's as if all the information about the three-dimensional interior of the black hole is smeared out and stored on its two-dimensional boundary. The holographic principle generalizes this. It suggests that everything that happens inside a volume of space, including you, your world, your galaxy, can be described by information living on the boundary of that space. The 3D world is a holographic projection of a 2D reality. This does not mean you are literally a hologram in the sense of a laser light show. It means that the fundamental degrees of freedom, the bits of reality, live in a lower dimensional space. Our perception of a third dimension, of depth, may be an emergent illusion, a clever reconstruction from this more fundamental, flatter reality. So we stand at a precipice. The solid ground of space and time has crumbled beneath our feet. We are left with these strange, ghostly pictures of what might lie beneath. A universe made of information. A cosmos woven from entanglement. A reality that is a quantum network of connections. A world that is a hologram projected from a distant boundary. These ideas are not yet proven theories. They're dispatches from the frontiers of human thought. But they all point in the same direction. That space and time are not the beginning of the story. They're the middle. They're the consequence of a deeper set of rules that we are only just beginning to decipher. What does this mean for you? It means that when you look up at the night sky, the vast distances between the stars may not be the most fundamental thing separating them. The true separation may be a lack of connection, a deficit of entanglement. It means that when you feel the relentless passage of time, you're not being carried along by a cosmic river. You are experiencing a macroscopic manifestation of countless, discrete quantum events, a statistical arrow pointing from a more ordered past to a more disordered future. You are a process, not a thing. It means that your very sense of self, your consciousness, your feeling of being a unified entity existing here and now, might be an emergent property of this deeper informational reality. You are a stable pattern, a complex resonance in the network of cosmic connections. What is space? It may be the language our brains use to interpret the web of quantum entanglement. What is time? It may be the way we perceive the universe's inexorable increase in entropy, the unfolding of its computational story. Are they real? This question itself has changed. It is no longer a question of absolute versus relational. It is a question of fundamental versus emergent. Temperature is real. You can be burned by it, but it is not fundamental. The image on your screen is real. It can make you feel joy or sorrow, but it is not fundamental. Space and time are real in the same way. They are the medium of our experience. They are the operating system of our perception. You cannot simply wish them away. The laws of Einstein's space-time govern your every move, every moment. But they're not the ultimate truth. They're shadows on the wall of Plato's cave. We have spent our entire history studying the shadows, mapping their behavior with incredible precision. Now, for the first time, we are beginning to turn our heads towards the fire that casts them. We do not know what we will find there. Perhaps a reality of pure information, a mathematical structure, a network of relationships so complex and so alien that our language of space and time will seem as quaint as the ancient belief in a flat Earth. The journey from Newton to Einstein to the quantum abyss has been a progressive stripping away of our intuitions. We lost the comfort of an absolute stage. We lost the certainty of a universal now. And now, we may be losing the stage altogether. This can feel unsettling. It can feel like a profound cosmic demotion. To be told that the very ground of your being is an illusion, a secondary effect, a hologram. But it can also be seen as something else, something liberating. If space is not fundamental, then the immense, crushing loneliness of the cosmos might be an illusion. We are not separated by a cold, uncaring void. We are connected by a web of information that is the very fabric of reality. Every particle in your body is entangled with particles across the universe, echoes of the singular state of the Big Bang. You're not a stranger here. You are a part of the whole, woven from the same quantum threads as the most distant star. If time is not fundamental, then the tyranny of its arrow might be softened. The past is not gone, and the future is not unwritten. In the block universe of space-time, all moments exist equally. Your life is not a fleeting spark. It is a permanent pattern etched into the four-dimensional fabric of what is. A song that, once played, exists forever in the symphony of the cosmos. We are explorers mapping a territory that may not exist. We are physicists writing equations about a world that is a translation of a deeper text. We are thinkers suspended between the elegant world of geometry and the chaotic world of the quantum. The final answer to the question, what are space and time, has not yet been written. It may be that the answer is not a statement, but another question, a deeper question. For now, you are here, and you are now. You feel the floor beneath you and the seconds ticking by. Cherish this illusion. It is a beautiful and powerful one. It is the story the universe tells itself about itself. And you are not just a listener to this story. You are a character within it. You are a thought in the mind of the cosmos. And you are the universe's way of beginning, just beginning, to understand itself.